Welcome to Energy Practice Problems. Let's check out our solutions here. So it says, first one, what are the two forms of mechanical energy? Those are just our good old potential energy and kinetic energy that we've been talking about this week. Number two, a basketball is raised above the ground, so it has 3 joules of PE. What happens to the potential energy as it falls towards the ground? And how much KE will it have when it impacts the ground? So yeah, if we have our basketball right here, as it's sitting at that height above the ground, it's got 3 joules of potential energy. As it falls, that PE will be transformed into kinetic energy. Otherwise, the PE will go down while the kinetic energy will go up. And how much kinetic energy will it have when it impacts the ground? Well, at ground level, the moment it hits, oh, that's a terrible picture, Welty. We'll do it better. Hold on. So here's the ground, and as it impacts the ground, its PE will be 0 because it's at a height of 0. So the kinetic energy there will be all 3 of those joules. We'll have complete transformation of PE to KE. Number 3, what does it mean to say that energy is conserved? So that just means our initial energy total is equal to our final energy. That is, we're not going to be losing any energy later. So if we actually use that basketball example, the initial energy is all potential energy. And as it hits the ground, all of those 3 joules will be converted to kinetic energy. We won't have any lost. All right, number 4, a bicycle has 600 joules of KE. If it doubles its speed, what is its new kinetic energy? So this is a little more thought than you might think here. So if we have 600 joules of KE at 1 speed, so if kinetic energy is 1 FmV squared, that number is 600. The question is, if I double my speed, that is, my kinetic energy would be 1/2 m twice the velocity squared, right? If I double the speed, right? I'm going to double it. 2v squared. What will that kinetic energy be? And at first glance, you might think it's 1200, but that is not the case. Since we're taking velocity squared, 2v squared is going to be 2v times 2v, which is 4v squared. So that kinetic energy will go up by 4 times the original amount, or 4 times 600 is going to be 2400 joules. And really the point of this question is, people think when they're driving, if they double their speed, that, oh, well, I'm just going twice as fast. But it's way more dangerous than that, because your car's kinetic energy will go up by 4 times the amount. And that energy, if you hit something, has got to go somewhere, and either into your car or into someone else's car. So don't speed, everybody. Obey the speed limits. Number 5, fill in the missing energies in the cartoons here, right? So let's take the ones down below here for a second. So we say the PE is 30 joules at this height. So regardless of being on a ramp, I still have 30 joules. The height is still the same. Here, again, it's going to be 30 joules at the top step. If I go down a step, then it's going to be 20 joules. And if they asked you right here, that would technically be 10 joules. All right, as this rolls off and falls, the KE will be 30 joules the moment it hits the ground. Right, our energy being conserved. If we look at our skydiver here, well, not our jumper, right, into this little bucket, it's so tiny, assuming he fits. So if he's got 15,000 joules of potential energy at the beginning, that energy is going to be converted to PE and KE as we go down. So, but remember, the total amount has to stay the same. So we're always going to have 15,000 joules here of total energy. So even right here, the total amount will be 15,000. So just because I have 11 to 50 joules of PE, well, if I subtract that from 15,000, I'm going to get 3750 joules of kinetic energy, right? Sorry, that didn't come out too good. And we get about halfway down, the total energy will still be 15,000 joules. If I have 7,500 joules of PE, then the other 7,500 joules will be KE. So I add up to be 15,000. Here again, the total amount will be 15,000. Okay, my energy must be conserved. So the kinetic energy at this point is going to go up, and it's going to go up to 11 to 50 joules if I do the math right. And then once he lands in the bucket, the moment he gets in there, his height is 0, but we're still going to have a total of 15,000 joules. Can't lose our energy. So that means our jumper will have 15,000 joules of KE upon bucket entry. Okay, let's keep going, I think. Yep, there we go. All right, so some practice problems here, I guess. We have a little more math to do. 6 just says, what is the potential energy of a physics book that's held at 2 meters? So yeah, we used to actually use a book. I haven't used a book in 8 years at least. But when we did, that was the mass of it. And if we do our calculation here, potential energy is mass times the acceleration due to gravity times height. So 2.25 kilos times our 9.8, and the units are just meters per second squared there, and height of 2 meters. So if I roll that out on my calculator, I'm doing it live. So I record this, 2.25 times 9.8 times 2, and that gives me 44.10 joules of PE. All right, 7, what is the KE of our Honda Civic here? And that's about the mass of a Civic, going 20 meters per second, which is 45 miles per hour. So K is 1 FMV squared, 1/2 the mass. Civic's about 1,500 kilograms. It's like over 3,000 pounds. And I need to square the velocity, which is 20 meters per second. So if I do 20 meters per second squared, 20 squared is 400, right? Times 1,500 times 0.5, and that's going to give me 300, I almost said 30, 300,000 joules of kinetic energy going down the road. All right, number 8, pig on the muddy hill. I'm going to draw it. Here's our pig on the muddy hill. So here we go. That's the pig. Perfect. Give him some legs there. Excellent. If you're having ham for Thanksgiving, you know. All right, sorry, vegetarians. 200 kilogram pig is standing on top of the muddy hill on a rainy day. Vertical drop of 30 meters. So pig has 30 meters above ground level right here. And, he's going to slide down the hill. And obviously that potential energy at the top of the hill is going to get converted into all kinetic energy at the bottom. So it says, what is the PE at the top of the hill? So we can do that. PE is mgh, multiplying our 3 numbers together. So 200 kilo pig, it's like over 400 pounds of ham, 9.8 meters per second squared, and pig is 30 meters up. That's pretty high for a pig. I don't know if he can get up there all by himself. 200 times 9.8 times 30. 58, right down here, 58,800 joules of potential at the top. All right, what happens to this PE? And what will the pig's KE be? We just kind of talked about that, right? So potential energy at the top of the muddy hill, and as he slips and slides down the muddy hill, that PE will be transformed into kinetic energy. So if we have 58,800 up here of PE, our kinetic energy at the bottom will also be 58,800. All right, assuming no friction there, reminiscent to our energy skate park being a little more realistic. So what's the speed at the bottom? Well, that's 58,800 KE is going to be 1 FMV squared. So if I do this, can I get a little more room here, folks? Yeah, we'll get a little more room. So that's going to be 58,800 joules equals 1/2 times the mass of the pig, which is 200, times v squared. So we have to solve for v. And so if we do 1/2 of 200, that's 100 divided into, divide both sides by 100 there. This will all cancel out. Divide that by 100. I'm going to get 588. So v squared will be 588. If I square root all that, so square root of 588 is, drum roll please, about 24 meters per second, which in terms of miles per hour is about 53. So not caught speeding this time, pig. All right, less under 55 miles per hour rate. All right, let's do our last one, number 9. And back to Galileo and free fall, right? So yeah, when he dropped things off Leaning Tower of Pisa, hey, how tall was the tower? How, things had potential and kinetic energy for sure. So don't do that. All right, let's sketch that in here. So we've got, here's the leaning tower. Give it a slight lean. I could import a picture, but we're just going to draw it out a little bit. By the way, if you didn't know, fun fact, the Leaning Tower of Pisa was leaning to fall over, and they actually put in foundation under this here years back. But not to straighten it out, because if the Leaning Tower wasn't leaning, nobody would want to go see it, right? True story. Okay, so they kept it leaning. So here's Galileo up here, and he's dropping objects off. So let's say he's got a 5-kilogram object, like 12 pounds or so, and they observe it hitting the ground, going 15 meters per second. So we want to know what the kinetic energy is down here of the object. So 1/2 mv squared is our Ke. So that's going to be 1/2 times the mass of the object, 5 kilograms. And it's going 15 meters per second. So we'll square that. So 15 squared, I know that's 225 times 5 times 0.5 equals. So that gives us a kinetic energy of 562.5 joules. What was the PE at the top, right? So obviously, we're a certain height above the ground. That object will also have potential energy. So we're assuming energy is conserved, so it will also be 562.5 joules. That was all transformed into kinetic energy as it hit the ground. And we know what height did he drop it from, right? So this would be, the PE would be mgh. And it looks like we're going to solve for h here, everybody. So if it's 5 kilograms times 9.8ers, all right, times h, and that's going to equal 562.50 joules. So 5 times 9.8 is 4.9. Oh, I lied. It's 49. It's 49. It's about 49. So if I divide both sides by 49, so 562.5 divided by 49 equals, so I get a height of the tower of about 11.48 meters. There you go.